Hello everybody. In this video, I'll explain the numerical problems on module 3 of paper 7. So for chapters band theory of solids, superconductivity and magnetic materials. Okay. So we shall discuss one after the other. So first problem is calculate the conductivity of pure germanium if the carrier concentration is 2.1 into 10 raised to 19 per meter cube. The mobility of holes and electrons are 0.4 meter square per volt second and 0.2 meter square per volt second respectively. Okay. So this is a direct problem. All the quantities are given here. So the suitable formula for this is the total conductivity of the intrinsic semiconductor is conductivity due to the electrons and conductivity due to holes. Okay, the sum of conductivity due to electrons and the conductivity due to holes, and the formula is like this: Ni, where Ni is the intrinsic charge carriers, the concentration of intrinsic charge carriers, E being the charge of an electron, mu n plus mu p, that is mobility of electrons and mobility of holes. Okay, so all the values are given to us. N is given. Okay, mobility of holes is given, mobility of electrons is given. So substitute all the values, you will get the answer as 2.016 mole per meter. Okay, moles per meter. Okay, so next problem. The thickness and area of silicon wafer are 0.35 millimeter and 1 centimeter squares respectively. Okay, calculate the current produced in it when potential difference of 2.0 volts is applied between its phases. The mobility of electrons and holes are 0.4 meter square per volt second and 0.2 meter square per volt second respectively. The carrier concentration in silicon is 2.1 into 10 raised to 19 per meter cube. So first list out the given values here. Okay. So thickness of the silicon is given here, 0.35 millimeter. Remember, this is given in CGS. We have to convert this into SI units. 0.35 into 10 raised to minus 3 meters you write down. D is equal to, thickness D is equal to 0.35 into 10 raised to minus 3 meter. And area is given as 1 centimeter square. That you write it as 1 into 10 raised to minus 4 meter square. Okay. Calculate the current produced in it. I is to be determined. Okay. I is equal to question mark you write down. And the potential difference is mentioned. Capital V is equal to 2.5 volts. You take a capital V as 2.5 volts. Okay. And the mobilities are given for both electrons as well as for holes. And intrinsic carrier concentration is also given. Ni is given. Okay. To solve this, take a basic formula, that is electrical conductivity is the ratio of current to the strength of the electric field. So substitute the value of current density as I by A according to the definition. Okay, and substitute the value of E as V by D. Okay, so E can be written as V, where V is the applied potential, D being the distance between the two plates or distance between the two parallel plate capacitors. We express the electric field in terms of capacitors here. Okay, so this is the general formula what we are going to use in our capacitors. The same formula we have to make use in doing this calculation. That is I, you are writing it as I by A, and E you are writing it as V by D. So D will be in the numerator. Okay, so I is to be determined in this problem. Okay, I is equal to, you just cross multiply it. I is equal to sigma into A into V divided by D. Okay, but sigma is not mentioned directly. Okay, so like your previous problem, we have to substitute the value for sigma as Ni into E mu n plus mu p and write down this A into V as it is divided by D. Now all the values are with us. So just substitute. Okay, Ni is given as 2.1 into 10 raised to 19. E is nothing but 1.6 into 10 raised to minus 19. Substitute the values of mu n and mu p, that is 0.2 plus 0.4, and area is given as 1 centimeter square, which is nothing but 1 into 10 raised to minus 4, and potential difference is given as 2.5 volts and the thickness is 0.35 into 10 raised to minus 3. So after doing calculation, we will get the current value as 1.44 amperes. Okay. So next problem is find the mobility of electrons in copper, assuming that each atom contributes one free electron for conduction. Resistivity of copper is 1.7 into 10 raised to minus 8 ohm meter. Atomic weight of copper is 63.54 AMU and its density is 8960 kg per meter cube. Okay. So Avogadro number is also given here, 6.025 into 10 raised to 26. Okay. The suitable formula, what is to be determined? First list out the given values. Resistivity, that is rho, is given to you. Okay. And atomic weight is given to you. Density is given to you. Avogadro number is mentioned in the problem. Okay. So first we have to see what is to be determined here. Okay. Find the mobility of electrons, that is mu is to be determined. So write down the first mu formula here, that is sigma is equal to n into E into mu. Okay. So sigma is equal to n into E into mu. This is to be determined. Mu is to be determined. Okay. So in this, what all the given values are there that we have to check out first. Sigma is not given directly. Instead, they have given a resistivity. So we can do the calculation of sigma because resistivity is a reciprocal of sigma. So we can write like this. But n is also not mentioned directly. Concentration of charge carriers is not mentioned. So we have to make use of this formula for calculating a concentration of charge carriers. Avogadro number into density divided by atomic weight into number of free electrons per atom. Substitute the value of Avogadro number. Okay, density is given here and also the atomic weight is mentioned. Number of free electrons per atom is 1 is mentioned. So do this calculation. Now making use of this calculation, okay, what is to be determined here? Mu n is to be determined. Mu n is equal to 1 divided by n E into rho. Take this to the denominator. Mu n is equal to 1 divided by n E into rho. Okay. Now we have all the values with us. Substitute. This we have calculated just now. Okay. Into the charge of an electron into the density which is given in the problem itself. After doing calculation, we will get the value as 0.004327 meter square per volt per second. Okay. So next problem, calculate the Hall coefficient of sodium if the number of free electrons per unit volume is 2.55 into 28. This is a direct problem. Everything is given for us. The Hall coefficient formula is RH is equal to minus 1 by NE. While solving the problem, you no need of using this negative sign because the negative sign indicates that the type of charge carrier present in the specimen. If the type of charge carriers are electrons, we will get it as negative. Otherwise, for holes, we will get it as positive. So while substituting the values, you can eliminate this negative sign. Okay, while writing the answer, you can eliminate this negative sign. So the concentration of charge carriers is given, substitute that value, and charge of the electron we know already. So substitute. So if after doing the calculation, we will get this as 2.447 10 raised to minus 10 meter cube per coulomb. Okay. So because the unit of n will be per meter cube. Unit of n will be per meter cube. So the answer of this one, Hall coefficient, will comes out to be, the unit of Hall coefficient will be meter cube per coulomb because the unit of this one is coulomb. So per coulomb you write down. Okay. Next problem. Calculate the Hall voltage developed in a germanium crystal of thickness 0.5 into 10 raised to minus 3 meter when a magnetic field of 0.7 Tesla is applied. The current density is 250 ampere per meter square. This should be meter square. By mistake it has come out to be 3 here. So please note it. This is ampere per meter square. And the electron density is 2 into 10 raised to 23 per meter cube. Okay. So write down the basic formula from your Hall coefficient explanation, that is EH, that is what I have written here is E Hall, that is electric field, that is Hall electric field, I have written as EH is equal to RH, that is Hall coefficient, into I into H, that is where H is the strength of the magnetic field. Okay. So now in order to calculate the Hall voltage is to be determined here. So in order to calculate Hall voltage, we have to use the formula, that is electric field is equal to V by D. Electric field is equal to V by D. So in order to get the Hall voltage, multiply this equation by D on both sides. Multiply this equation by D on both sides. We will get EH into D, that is nothing but the product of these two is nothing but voltage, that is Hall voltage, RH into I into H into D. Okay, therefore VH is equal to I into H into D divided by NE. Now I have written RH as NE in this formula because RH is not mentioned directly. Instead they have given a concentration of charge carriers here. So you express this RH as NE here. Now we have all the values with us. I value is 250, H is 0.7, okay, and D is 0.5 into 10 raised to minus 3. Okay, N is given as 2 into 10 raised to 23. E value you substitute. You will get the answer as 2.7 into 10 raised to minus 6. Okay, you will get the answer as 2.7 into 10 raised to minus 6 volts. Okay, so that I have expressed it as 2.7 into 2.7 microvolts. Okay, so the answer is 2.7 microvolts. Now let us calculate another problem, that is calculate the number of electron hole pair. Calculate the number of electron hole pair per cubic meter in an intrinsic silicon at 37 degrees centigrade. Okay, at 37 degrees centigrade. The value of its forbidden energy gap is 1.12 electron volts. The number of electron hole pair per cubic meter in pure germanium crystal is 2.5 into 10 raised to 19 at 27 degrees centigrade. Given energy gap for germanium is 0.72 electron volts and the Boltzmann constant is mentioned. Now read the problem carefully. What is to be determined, that we have to list it out. So what is to be determined here is we have to determine the N value, that is the concentration of electron hole pair in the silicon atom for particular temperature they have mentioned. Okay, 37 degrees centigrade they have mentioned. So this you convert into kelvins. 37 plus 273, you do it and keep it aside. Okay, and energy gap is given for silicon here, 1.12 electron volts. And similarly for germanium they have given the concentration of charge carriers at 27 degrees centigrade. Again you convert this into kelvins. 27 plus 273, energy gap is also mentioned here and Boltzmann constant is given. Now we have to determine this value. The formula, general formula for Ni, from our derivation we will get this value. Okay, and all this constant I have taken it as A here, leaving this T to the power 3 by 2 because for different temperatures is asked in the problem. So T to the power 3 by 2 retained and the remaining things I have taken it as constant and Eg by 2 kT. Okay, now you find out this value for germanium and find out the value for silicon. Take a ratio, we will get this because for germanium it is mentioned, for silicon this is to be determined. Okay, so first you write down for germanium, write down the concentration of charge carriers which is given as this much. Okay, constant you write down as it is. Okay, the temperature is 27 degrees centigrade, so this becomes in kelvins it is 300 to the power 3 by 2 e to the power Eg by 2 kT. Eg is how much? It is given as 0.72 electron volts. This needs to be converted into joules. So you write down 0.72 into 1.602 into 10 raised to minus 19 divided by 2 kT. Write the, substitute the value of Boltzmann constant in temperature as 300. So do this calculation, keep it the e to the power value as, and this value comes out to be 13.93, so minus 13.93, call it equation number 1. Now you do a similar type of calculation for silicon. Okay, so for silicon you calculate, Ni is not given, so you write down Ni as it is, A value, and 37 degrees centigrade is given. So write it in terms of kelvins as 310 T to the power 3 to the power 3 by 2, 310 to the power 3 by 2 into, so similar type of calculation, that is I have done it directly, and remember the energy gap is given as 1.12. So here what you will substitute, 1.12 into joules is to be converted here. Okay, in terms of joules it has to be converted because it is given in electron volts. So after doing this type of calculation for silicon, you will get it as minus 20.97. Call it equation number 2. Okay, dividing equation 2 by 1. Okay, take a ratio of these two, AA gets cancels. Okay, and write down these values, and I have eliminated these negative signs by writing it in a reciprocal manner. See, this one I have taken to the numerator and this one I have taken to the denominator so that I can eliminate the negative values. If you have a calculator, you can do the calculation directly including negative signs also. Okay, so please write down all the corresponding values. Do the calculations very carefully because the powers, too many powers are involved here, and exponential quantity is also involved here. Check out the values for each of these things and do this calculation separately and write down. You will get it around this much, and do this calculation, you will get it around this much. Then find out a product of that, and unit of this will be per meter cube. Okay, unit of this will be per meter cube. So the answer comes out to be 2.299 into 10 raised to 16 per meter cube. So this is the concentration of electron hole pair in silicon. Okay, so next problem. Okay, the critical magnetic fields at 6 Kelvin and 8 Kelvins for superconducting alloy are critical magnetic fields are given. Okay, so two values are given here, 7.616 into 10 raised to minus 3 ampere per meter and 4.284 into 10 raised to minus 3 ampere per meter respectively. Determine the critical temperature and critical field at 0 Kelvin. Okay, critical temperature and critical field is to be determined. So the general formula for critical magnetic field is Hc of T is equal to Hc of 0, 1 minus T by Tc whole square. Hc of T is critical magnetic field at a given temperature. This is at 0 Kelvin and Tc is nothing but your critical temperature. This is to be determined, and Hc of 0 at 0 Kelvin is to be determined. Now substitute the values here. All the values are given for you. Okay. So Hc of T for two values for two different temperatures are given. So you have to write down two equations corresponding to this temperature and this temperature. Okay. So write down two values. So this is given, critical magnetic field is given. The left hand side you write down here. Hc of 0 you write down as it is 1 minus 6 divided by Tc you retain as it is. Similarly, write down the another equation, call it equation number 2. Divide equation 1 by 2. After dividing equation 1 by 2, you will get this as I said. Just write down the ratios here. Just you divide these two equations. This divided by this is equal to this, and this gets cancelled. This divided by this. Okay. So remove these Tc squares by taking a LCM. Okay. By taking a LCM and cancel it out, whichever which get cancels. Okay. So the next equation reduces to this form. Okay. Cross multiply it and do the calculation carefully. Okay. So see the substitutions carefully here. Okay. Cross multiply. You will get first DC square, then you calculate Tc. Okay. Now you substitute this Tc value in any one of the equation. Either in equation 1 you substitute or in equation 2 you substitute. You will get a critical magnetic field at 0 Kelvin. Okay. So take any one of the equation. Now I have selected equation number 1 for doing this calculation. Okay. Substitute it, and Hc of 0 is equal to cross multiply it, and you will get this answer as 0.0119 Tesla. Okay. So next problem. Iron contains 10 to the power 29 atoms per meter cube. Okay. The magnetic moment of each atom being 1.8 into 10 raised to minus 23 ampere meter square. Okay. Ampere meter square. Treating iron as paramagnetic. Okay. Treating iron as paramagnetic finds its susceptibility at 300 Kelvin. Okay. In derivation of Langevins theory of paramagnetism, we have arrived at the expression for susceptibility as chi is equal to mu naught n m square divided by 3 kT. Okay. So now all the values are given to us. We can do this calculation. Mu naught is nothing but 4 pi into 10 raised to minus 7. Okay. Mu naught is nothing but permeability at free space. So 4 pi into 10 raised to minus 7. Okay. And n is given as 10 to the power 29. per meter cube. You substitute that value. Magnetic moment is also given here, 1.8 into 10 raised to minus 23 square, under square it is, divided by 3, and Boltzmann constant. This K is nothing but a Boltzmann constant. You substitute the Boltzmann constant value. Okay. So into the, for temperature, for what temperature it is to be determined? For temperature 300 Kelvin. So write down the 300 here and do calculation. After doing calculation, we will get this value as 0.0033 susceptibility, and no unit for this one. So this is all about the problems on module 3.